मैम ने ज्वाइन कर लिया? लक्ष्मी मैम ने? हेलो।
नहीं सर, अभी नहीं शायद।
Hello,
मैम आ गई
I've
हैं।
ओके।
joined. I've already
गुड
joined.
इवनिंग मैम।
Good
ओके
evening.
ओके मैम, ओके मैम। ओके। सो हिमांशु सर, रिकॉर्डिंग स्टार्ट कर दीजिए।
थर्ड है सर।
It's already started. Recording started. You start the session.
It is started.
ओके। Good evening and a very warm welcome to all the dignitaries, expert speakers, and participants joining us today. On behalf of the Department of Electronics Engineering, MITS Deemed University Gwalior, I feel honored to welcome you to the AICT sponsored Atal Online Faculty Development Program on Emerging Frontiers in Quantum Technology and Communication, which is scheduled from 15th to 20th December 2025. We are very grateful to the AICT Training and Learning, that is Atal Academy, for sponsoring this prestigious program. Now I request all participants to kindly keep their microphone muted and use the chat box for any technical queries during the sessions. Now, I request the head of the department, Dr. Lakshmi Srivastava Madam, to brief participants about the Institute, Department of Electronics, and Atal FDP. Ma'am, over to you.
Thank you, Mukesh. Good evening, all. A very warm welcome to all the dignitaries, expert speakers, faculty members, researchers, and participants joining us today. On behalf of the Department of Electronics Engineering, Madhav Institute of Technology and Science, Deemed University, I welcome you to all to the AICT sponsored Atal Online FDP Faculty Development Program on Emerging Frontiers in Quantum Technology and Communication. It gives me immense pleasure to briefly introduce about the MITS Gwalior and the context of this AICT Atal FDP program. MITS Gwalior, which was established in 1957 by Sir Jivaji Rao Scindia, is one of the premier technical institutions in the country. In 2024, the institute is accredited with a NAC A++ grade and was granted deemed university status under the distinct category by the Ministry of Education, Government of India. The institute offers UG, PG, and PhD programs across major engineering disciplines and is committed to quality education, research excellence, and innovation. The Department of Electronics Engineering, which was established in 1987, plays a key role in this mission. The department offers UG program with an intake of 120 students, PG programs with an intake of 25 students, and also the PhD program. The electronics engineering program is NBA accredited till 2028, reflecting a strong academic standard. The AICT Atal Academy is a significant initiative focused on faculty empowerment, skill enhancement, and quality improvement in higher education, aligning academics with emerging technologies. In this context, the Atal FDP on emerging frontiers in quantum technology and communication is highly relevant as it addresses quantum computing, quantum cryptography, secure communication, and future communication systems. Now, I am confident that this FDP will be academically enriching and professionally rewarding for all the participants. I extend my best wishes for the successful conduction of the program. Now, thank you, all the team members of this program and all the participants. Thank you.
Thank you, ma'am. Now, to formally introduce the FDP, its objectives, and the topics to be covered. I now invite FTP coordinator Dr. Vandana Vikas Thakre, Professor and Head, Department of Electronics and Telecommunication Engineering. Madam, over to you.
Thank you, Mukesh. Am I audible?
Yes, ma'am.
Okay. So, very good afternoon to all of you. Being a coordinator, I welcome you all the participants joining us today. Myself, Vandana Vikas Thakre, on the behalf of MITS DU Gwalior and on the behalf of my organizing team, welcome you all to the AICTE sponsored Atal Online FTP on emerging frontiers in quantum technology and communication. Being a coordinator, it's my privilege to brief about the FDP. This FDP aims to provide an in depth understanding of the latest advancements in quantum technology and its applications in communication systems. With the rapid evolution of quantum computing, cryptography, and secure communication, proposed FDP will provide all the participants with essential knowledge and skills in the cutting edge domain with different and various objectives through this FDP. The FDP aims to introduce fundamental concepts of quantum mechanics relevant to communication systems, which is the need of the time. It also explores quantum computing, quantum cryptography, and quantum key distribution in detail. The FDP also familiarizes our participants with challenges, opportunities, and future scope of quantum technology. And parallel gives an exposure to quantum simulators and experimental tools. In this FDP, we have eminent experts who will cover versatile topics related to quantum technology. Therefore, all the participants will gain insight into fundamentals of quantum mechanics and quantum information theory, quantum states and qubits, quantum secure communication and sensing, quantum gates to algorithm, QKD protocol and QRNG protocol, quantum communication over telecom fibers, and optical networks. It is to inform you all that we have valuable expert sessions for coming 6 days. We are privileged to host renowned experts from IITs, international universities, and industries. We have speakers from USA, Spain, IIT Delhi, CDAC, C. and QPI AI. It will ensure a strong blend of theory, research, and industrial perspective to all our participants. This FDP aims to prepare participants for quantum enabled secure communication systems, 6G networks, and future research challenges. I hope you all will be having a great learning ahead and you will all enjoy the knowledgeful sessions. Good luck. Now I request the co-coordinator Dr. Mukesh Mishra to brief participants about the expected outcomes, expert sessions, and important rules related to attendance and certification. So this is all from my side. Thank you so much and have a happy learning. Dr. Mukesh, please.
Uh, Thank you, ma'am. Now, as a co-coordinator, I am going to brief participants about the expected outcomes, about the sessions, and important rule related to the attendance and certifications. Okay, so this FDP is actually designed not only to enhance theoretical understanding, but also to ensure practical skill development and future readiness. So at the end of this FDP, we are expecting that you can develop quantum competency in qubit, quantum information theory, and communication system. You will also able to gain exposure to quantum simulators, algorithm, and quantum machine learning, build expertise in quantum cryptography, especially QKD. Those are relevant to the future 6G networks, and also strengthen research and innovation readiness for academic and industrial applications. Now there are total 13 sessions are scheduled under this FDP, and each session will be conducted by domain experts. So active interaction and participations during expert talks are highly encouraged. Now there are some attendance and certification rules. So one by one I am going to discuss. So first one is the attendance, assessments, feedback, and certifications will be managed as per the Atal guideline. So participants must ensure minimum 80% attendance. Mandatory MCQ test will be conducted at the end of the FDP. Participants must score at least 70% marks in the test to be eligible for the certificate, and attendance will be monitored session wise using Google Sheet. I will share this Google Sheet and you have to just mark your attendance in front of your name. And certificates will be issued only through the AICT Atal portal to eligible participants. And one more thing, suppose if a lecture is cancelled due to a last moment issue on the part of the speakers or from our end, so we will reschedule it for another day. And we request all participants to join session on time, mark their attendance correctly, and actively engage throughout the FDP. And now, once again, we thank AICT Atal Academy, the MITSDU Gwalior leadership, our distinguished experts, and all participants for being a part of this FDP. With this, we formally conclude the inauguration session and proceed towards our first lecture of the program. Thank you, and have a fruitful learning experience. So we will wait for some time. When our speaker join, we will start our first lecture. Am I audible? Hello?
Yes.
Yes, sir.
Okay. Okay. So now I'm going to share the attendance sheet. So in this attendance sheet, you are required to mark your attendance session wise. And to mark your attendance, please write 1 at the session column. All the name are arranged alphabetically. So if you don't find your name, so you can mail us. We will add your name. Now, Professor Arun Pati sir with us. So, uh, am I audible, sir? Arun, sir?
Yeah, yes, I can hear you.
Okay, sir. So, good evening, respected sir. A very warm welcome and thank you for joining us. It is my great privilege and honor to introduce today's distinguished speaker, Professor Arun Pati, an eminent expert in the field of quantum theory and computation. Now I'm going to introduce sir. Professor Arun K. Pati has made many pioneering contributions in the area of quantum computation and quantum information. He has been working in the area of quantum science quantum computing, and quantum information over last 35 years. His seminal contribution include the no deletion theorem, no hiding theorem, no masking theorem, remote state preparation, and stronger uncertainty relations. His research paper have featured in Nature, Science, Scientific American, and Nature Asia. For his original and creative contributions, he has received many awards. This includes the Indian Physical Society Award for Young Scientist, Kolkata in 1996, Indian Physics Association Award for Young Physicist of the Year, Mumbai 2000, Samantha Chandra Shekhar Award for the year 2009 from the Odisha Science Academy, India, and the Distinguished Alumni Award from Behrampur University, Odisha. He is an elected fellow of the Indian Academy of Science, Bengaluru, and also fellow of the National Academy of Science, Allahabad. He has a JC Bose National Fellow in 2019. He consistently ranks in top 2% scientists in the world by the Stanford University. He also figure in number 1 position as world's famous quantum information scientists. He is regarded as the father of Indian quantum computing. So this is all about the Professor Arun K. Pati, sir. Respected sir, the participants are eagerly looking forward to your talk. Now may I request you to please begin the lecture. Over to you, sir.
Yeah, thank you very much for your kind introduction. And thanks to Dr. Mishra for inviting to this event. Let me start sharing my screen. I don't see my file, I don't know why. So this one. I don't see my PPT, I don't know why. So maybe I can start from here.
Sir, if you can share your PPT, so from here we can.
Yeah, usually it shows, but somehow not today, not showing. I don't know why. So. Okay.
Okay, sir.
Can you see now?
Yes, sir.
Yes, sir, it is visible.
Is it full screen?
No, sir, not now. It is full screen, sir.
Okay, very good. Okay.
Okay,
So good evening, everyone, and I'm going to talk about quantum computing and quantum technology. So currently, I am at the Center for Quantum Technology at KIT University of Bhubaneswar, Odisha. This is a new center announced recently, and as already mentioned, I've been working in this field almost for the last 35 years. And what I'm going to tell you today is kind of, I will give a brief overview of this topic and why this field is, exciting and why this is interesting. And you will see that even though this field is there for last 35 to 40 years, over last 10 years, a lot of things, on technology side, on experimental side, a lot of development has happened. So I will also try to tell you those, developments, but I will not go into too much technical detail. I'll this kind of, brief overview. Okay, so why not moving down? Okay, a bit slow. Okay, can you see now? Next slide.
Yes, sir, we can see. 3.
Okay. So yeah, so quantum information technology, as you see, is a quite vast topic. Under this umbrella, you have several things, but broadly you can classify it 4 kind of themes. One is quantum computing, and second is quantum communication. Third is quantum metrology and sensing, and fourth is quantum hardware and materials. And if some of you might have noticed that National Quantum Mission, also started by Government of India, Department of Science Technology, they also classify. They've actually made 4 thematic hub, essentially based on these 4 themes. So today I'm going to talk about the first 2 part, quantum computing and quantum communication. I will not have time to go through this quantum metrology and quantum hardware side. Okay, so before I go to talk about quantum computing, I will tell you how classical information you manipulate. So basically, in classical world, you store information in strings of bits, and at any given time, your classical bit can be in 0 or 1. And all present day computer, whether laptop or mobile or your desktop, they store information on transistors switching between on and off states. Any 2 distinct state, you can identify a 0 or 1, and that represent 2 possible state of a classical bit. Then you do various tasks according to classical laws of physics. When I say classical laws of physics, could be your Newton's law or your Maxwell's equation and things like that. But what you notice is you never find your classical bit in combination of 0 and 1. At any given time, your bit can be only 0 or 1. Okay. Now, coming to quantum computing, historically, this all started way back in 1982 when Richard Feynman, one of the greatest physicists of last century, he tried to ask the following question: that what can happen if you store information in 2 distinct states of a quantum object, like spin of electron or polarization of photon or energy level of atom and so on. Okay, so he just out of curiosity, or maybe he had some intuition at the time, he raised this question, but then he did not pursue too much along that direction. So in 1985, David Deuce, who is a British physicist, he took this idea very seriously, and he realized that if you exploit so-called quantum mechanical superposition principle, then you can do something different than no classical computing can do. Okay, so he realized that quantum mechanical superposition principle allows a new way of storing information, and quantum computer basically device that perform computation using principles of quantum theory, the ultimate theory of nature, as we know, because quantum theory is the basis of all modern science. Whether you think of condensed matter or nuclear physics or particle physics or even string theory, any modern physics you think of, quantum mechanics is the basic thing that you have to learn, right? So he took this idea seriously, and you can say that the idea of quantum computer was originally due to David Deuce. Okay, and that is the main reason why he is also regarded as the father of quantum computing. And there is another motivation when you see that it's something to do with Moore's law. So it tells you that every 24 month number of transistors double. So if you see the trend, by 2030, this trend will tell you that you need transistor that will be about 2 nanometer distance, which is basically 4 atomic distance. And you know that at atomic scale, once you reach this micro scale, your classical physics will not be applicable. So your classical physics will break down, and you have to apply quantum mechanics to store and process information. But then this is not the so-called, very deep motivation. This is kind of because this so-called Moore's law is not a kind of fundamental law, like Newton's law. It is kind of empirical observation, and it was stated in this fashion by Morse in many years back. But this is kind of historical motivation. People thought, okay, you need quantum mechanics to do something at that scale. Okay. So if you ask the question, classical versus quantum computing, what are the key things you need to know? You need to know about the qubit, you need to know superposition, you need to know entanglement, quantum gates, and so on. And if you ask why quantum computing matters, because quantum computing can solve certain complex problems exponentially faster than classical computers. And that can revolutionize fields like computing, quantum chemistry, drug discovery, material design, machine learning, and artificial intelligence. So all the information era you see currently, it is going to impact all those directions. So, and this is going to open new frontiers in computation and scientific discovery. So coming to quantum bit, already you know how classical bit look like. Classical bit can be, as I said, could be only 0 or 1, but your quantum bit can be also in 0 or 1, but then because you have this superposition principle, you can have a state which is both 0 and 1. Why this happens? Because if you store your classical bit value like 0 or 1, like a spin half particle in a like electron spin, you say, okay, if electron spin is up, it is 0, if it down, it is 1. But we know that electron can also remain in a linear combination of up and down, like alpha up, beta down, and alpha beta are complex amplitudes. So because of this superposition principle, you have a state which is kind of alpha 0 plus beta 1. So you see this state is neither 0 nor 1. It is both 0 and 1 with some amplitude, right? So this is basically a qubit. And this qubit, you can think of as electron spin, or you can also think of like photon polarization or atomic level. In any two distinct state you can identify for a quantum system, and that can represent a quantum bit or qubit. Okay. So you see that there is inherent parallelism that comes into play, and that is responsible for new kind of computation. Okay. So this is what I said. You identify two distinct states, up and down. This is my 0, this is my 1, and then by superposition principle, I have this alpha up, beta down. Okay. And this is state of a qubit, But then if I want to know how much information is there, then I have to do a measurement. But then doing measurement will collapse the state to either up or down. That will give only one bit. So even though this quantum state qubit has a potentially vast amount of information, but at the end of the day, if you want to read out, you will get only one bit. Okay, so from given for any quantum bit, you can extract only one classical bit. Okay, but then you exploit this to do something, and at the end you do measurement and read the answer. Okay. Now, if you think of two quantum bit, let us see what happens. So we know that two classical bit can be in one of the four logical states, like 0, 0, 0, 0, 1, 1, 0, 1, 1. And same thing will also can happen for two quantum bit. But then because of superposition principle, you can have, say, situation where your two quantum bit can remain simultaneously in all four logical states. Okay. So this is not just this or this or this or this, but it is a situation where you have this and this and this and this, So that is the inherent parallelism which allows you to access all four logical states in one go. Okay. And these things, get enhanced if you think of a, n quantum bit. So in classical computer with n bit, at any given time, your n bit register can be in one of these possible logical state, but quantum bit can be in all those logical states, which is exponentially vast. For n equal to 300, this is roughly 10 to the 90, which is more than the number of universe, very more than the number of atoms in a known universe. You see how vast this actually explodes. So quantum computers take the advantage of this exponentially massive parallelism that you see in this number of logical state, and that basically tells you that how the quantum computers have become more powerful, Okay, so what can you do with quantum computing? So technological revolution from quantum computer may allow to solve problems that are too complex for classical computer. And in early days, only few things were known, like Schur's algorithm for prime factorization and Grover's algorithm for database search, and then Deuce-Deuce algorithm for deciding nature of some function. Okay, these are three famous algorithms you might have seen in textbooks, and it is quite a challenge, to discover something new, new algorithm in quantum computing, because it's not that quantum computer can do everything in an exponentially faster manner. No, not that. Quantum, there are certain tasks which can be done exponentially faster. Something can be done in maybe in politically faster, and so on. It is not, and it is also not true that everything can be done efficiently. No, you have to figure out. You have to discover what can be done more efficiently on a quantum computer. Because after all, if you build a quantum computer, that will be very expensive. You don't want to solve trivial problems which you can do on a classical computer, and you spend a lot of money in doing the same thing in a quantum computer. So quantum computers are very, very specific, kind of task-oriented computer which you need for specific purpose. Okay. So, but then there is a lot of hope. So that is why over the last 10 years, there is a global race to build quantum computer, and that has been race of 21st century. And this is a very difficult and ambitious challenge. And as you see, this can change or revolutionize future computers, starting from, this will have a lot of applications, starting from healthcare to defense, finance, chemistry, material development, software debugging, aerospace, transport. And as I said in the beginning, the speed and power of quantum computer actually comes from the situation, from the fact that your quantum computer can remain in multiple quantum state, and that occurs only at quantum level, and that is the main reason why you need to bring quantum computing to commercial reality, and we need a extraordinary team to put their efforts, and that is where a lot of companies are investing a lot of money. So if you see the timeline, the global race actually started like in 2016 by IBM. They announced about 4-qubit processor, and then by just 1 year after, they announced about 17-qubit. After 3 years, they announced about 65-qubit processor, and so on. You see, the number of qubit keeps on increasing, and over the last 10 years, lots of companies, several companies have invested heavily in this, and often you see two phrases, in literature. One is something called supremacy and quantum supremacy and quantum advantage. So if you say that your quantum computer can solve a problem that no classical computer can do in any feasible amount of time, whether you can say that is useful or not useful, don't worry about that. But you can say that you can do, solve in a feasible time compared to classical computer. You say, okay, my quantum computer has a supremacy, and something similar term often people use, and that is called quantum advantage. If you can demonstrate that a quantum computer can solve a problem faster than classical computer, you say it has advantage. Okay, so the first supremacy claim came by from Google, and they claim that with 54 qubit they could do something in 200 seconds, whereas best supercomputer classically will take about 10,000 years. So you see the power of quantum computer. Just 1 year later, Chinese team, they also claim that they can do something, on quantum computer, but classical computer will take about 10 billion times. Sorry, 10, and that is 10 billion times faster than Google's processor. So, and this is slightly, even more claim. I mean, more so-called, surprising claim that they could do the task in 200 seconds, and the same thing would take about 2.5 billion years in a classical computer. So you see, these devices really, demonstrate so-called quantum supremacy. And this year, Microsoft, they announced about 8 qubit major qubit processor, and then IBM announced about 1386 qubit. And very recently, just few months back, this group in Harvard and MIT, they built about 3000 quantum bit, and that could run for more than 2 hours, which is very impressive. And then the Caltech group, they did design about 6100 number of qubit with the cesium atom, this atomic quantum computing. And you see the progress is quite extraordinary in that sense. But then you see a lot of challenges also in quantum computing, and I will highlight some of the challenges. One is so-called scalability. So current devices are mostly noisy, so you need to go beyond noisy intermediate scale quantum computing era, so-called NISQ era, because if you want to build a full-fledged quantum computer, you have to go something like several thousand to a million qubits. So if you reach that level, then you can say my quantum computing is really scalable, which is still far away. We are still far away from that. And second challenge is decoherence and noise, because if you build a quantum computer, your qubits should have coherence time much longer, so that you can do all your gate operation within that coherence time. Okay. Once start decoherence basically means that your quantum system loses coherence. Coherence is again connected to quantum superposition. So if your system start decohering, your qubit will lose all its power, or so-called benefit. So you don't want to lose those benefits. You would like to do all the operation within the coherence time. So how to improve the coherence time so that you can improve the stability? Okay, that is second challenge. Third challenge is building fault-tolerant quantum computer. So currently we don't have that. So, and they're mostly noisy, mostly error built into that. So you need, but at the end of the day, at some point in future, you need to build a quantum computing device which has inbuilt error correction. Okay, so that is still quite a challenging task. And you need to develop new algorithm, and you need to demonstrate for more practical quantum advantage cases. You need to figure out which cases you can see actual quantum benefit, quantum advantage. So those are challenges are there, but progress is quite impressive, as I said. Okay, now in second part of my talk, I will try to focus on quantum communication side. That is again a vast area, and a lot of things has happened over last 30, 40 years. But before I talk about quantum communication, I need to tell you about so-called the notion of entanglement. And the entanglement notion was first introduced by Schrodinger, the same person, you study in your MSc, so-called Schrodinger equation. The same person, Schrodinger, he had introduced this notion of entanglement in 1935. And at that time, he could realize that entangled states are something you don't see in classical world. They have some strange feature you don't see in day-to-day life or in classical world. So in fact, he was so much obsessed or impressed by this by his own discovery, that he said entangled states are really telling you something very deeper. They tell you that there is much deeper than what you currently understand, at that time. So things were developing at that time. 1930, quantum mechanics were developed in 1925, right? So 25 to 35, just within 10 years, he could realize that entangled states are going to play a very major role. And in the same year, 1935, Einstein products Kirojan, they use these entangled states to argue something to do with incompleteness of quantum mechanics, because Einstein was kind of very, he had a world view which is more realistic, more classical, like, even though he played a very major role in development of quantum mechanics in early, like old quantum theory, starting from photoelectric effect and other things. But when modern quantum theory was developed by Schrodinger, Heisenberg, and others, he was having a lot of reservation, in the sense that he was not very happy with probabilistic interpretation, he was not happy with quantum measurement, and so on. So he thought maybe there is something more deeper than quantum theory, and quantum theory is not a final theory, not a complete theory. So he tried to propose a kind of Gedanken, experiment where entangled state display very strong correlation between space-like separated particles, and that leads to some kind of contradiction. And he said that, okay, I'm not going to again tell you the PR paper, but basic, philosophy, I'm trying to just tell you the philosophy is, you are trying to argue that there is something missing in quantum theory, basically, okay. But now, over the last 30 years, what our community trying to do is, you are trying to use these entangled states, okay, and the spooky action that the entangled state display, a strong correlation they display, to do quantum computation and quantum communication. So that is the beauty of this entangled states. So we can do something which is not possible in classical world, okay. So coming to entanglement, mathematically there is a very rigorous way to define it. Basically, it tells you that if you have two or more number of particles, and the composite state of the whole system cannot be factored into the wave function of this first times wave function of the second times the tensor product, okay. So if you cannot write this wave function times this wave function, then that is an entangled state, okay. So these entangled states are having some kind of strange correlations between them, and the individual entities are not independent. They are linked in a strongest possible way, that even if they are far apart, okay, they will still feel as if they are single, okay. That means if you prepare an entangled state, like two particle entangled state in your lab, and you keep one in your lab and take the other particle to, say, New York, or maybe to another planet, they will feel like as if they are single entity, they are so strongly correlated. And this quantum entanglement is another weirdest feature of quantum world. And as I said, we allow, and this allows us to do something amazing, which are otherwise impossible. And let us see what we can do with this. So before I tell you a few things about quantum entanglement and their application, I will tell you even something more interesting about quantum information. Quantum information stored in quantum bits, they maintain some kind of privacy. Privacy in the sense that if you have stored some information in your qubit, and I come and try to, read it, or try to copy it, or try to, temper it, or try to manipulate it, it is not always allowed to do that, So they don't reveal they don't reveal the information that is there inside the qubit, So in that sense, they maintain the privacy, So the first result was so-called no cloning theorem due to Reuters Jurek in 1982. So this tells you that if you store information in a quantum bit or qubit, only the person who has stored the information, only he or she can make a copy. Nobody else in the world can make a copy, okay. So this is simply prohibited by the laws of quantum mechanics. And similarly, we discovered in 2000 that if you store information in quantum bit, then it is not possible for somebody else to delete it, So you cannot delete the information. And no-hiding theorem discovered by myself and my collaborator in 2007 that tells you the following: that suppose you have information in a quantum bit and something happens to your system, and then you start losing coherence and you start losing all the information. At the end, the state becomes completely independent of the initial state. Okay. So you can think of a situation where initially your qubit like say alpha 0 plus beta 1, and then after something happens to the system, your state becomes completely random state, like say I by 2. Okay, identity means just 1001 in case of a qubit, so this I by 2 is called complete random state, and this has no information about the input state. Okay, then what happens? Then we proved that if something is missing from the original, then you can find the information in the rest of the subsystem. Okay, it's not actually lost, but it simply goes from here and remains in some other part of the universe or some other part of the world. Okay, and no masking is very recent result proved by myself and my collaborators again in 2018 that had to do with something different than all these previous three things, that is the following. So let me explain a little bit about this. So, so typically what you do in quantum information is you store information in physical system, like in spin or electron or proton polarization, as I said in the beginning. So you need a physical system. But what we ask is the following: that is it possible that you take the information, okay? Initially, of course, they are in some physical body like alpha 0 plus beta 1, but then you bring an additional system, okay, like another qubit, and do some interaction between these two qubit, and then this information which is originally in one part of the qubit, it simply goes and remains in the correlation, but not in this first qubit nor the second qubit. So basically, you put a mask here and put a mask here, so that if somebody comes and see, look at this first qubit, there's nothing here. If somebody comes and look at this second qubit, nothing is here. Okay, like put a mask. Okay, but it's there in correlation. Okay, in quantum entanglement. Is it possible? Had this been possible, you could have a different different way of storing information. Okay, which is not there in classical world. But then we proved that no, this is not allowed. Not allowed. Within this within this two-party correlation. But if you bring third, fourth, and say n number of qubit, then you can have a situation where this is allowed. So that means if you go to more than 2, it is possible to mask. So you can have a like 1, 2, 1, 2, 3 qubit, and then you can do something, and then information is in this correlation here, but not here. Okay, so that is allowed, but only this two-party is not allowed. Okay. So these are called no-go results in quantum information. So as I said, the first no cloning is impossible to make a copy of unknown qubit. Non-deleting tells you impossible to delete one copy from two unknown qubit. No hiding tells you if information is lost, it moves to another subsystem and cannot be hidden in the correlation. So no masking is again tells you that it is impossible to keep information in the correlation. Okay. Now, why these are important? Because these no-go results are something to do with, it is like telling you the rules of the game before you start manipulating quantum information. It is like, suppose you purchase a new car, before you go on the road and drive it, you should know the rules, what is allowed, what is not allowed, So it is like that. It is a set of guidelines that, okay, this is allowed, this is not allowed, this is, you can do, this you cannot do. So you should know what are the things that you cannot do with quantum information. Okay, that is first thing. Second thing is, with these no-go results, you might think that they are kind of limitations, but they're actually providing you inbuilt security to information stored in quantum computer. Like suppose somebody stored information in a quantum computer, only you can make a copy of the file. Nobody else in the world can come and make a copy of the file, So there's a complete piracy issue will disappear, if you want to build a quantum computer. And and this no cloning, no deleting also has important application in quantum key distribution, quantum communication, and so on. Okay, so there's a lot of applications of these results. Okay, so in quantum information, I just said quite vast area. So basic goal is how well you can store, process, and transfer quantum information using principles of quantum mechanics. That is the main goal. And in quantum mechanical features like superposition, entanglement, non-locality, these features you can exploit for practical applications and for doing imaging tasks which are impossible otherwise. So coming to quantum communication, you can ask what this scene looks like. So basically, you have two person, Alice and Bob. They are far separated, and Alice is in her laboratory, Bob is in his laboratory. So they are connected by quantum channel, basically entangled state, and they also have access to classical channel. Classical channel is basically your telephone or your mobile phone or internet, anything you can think of. And then Alice and Bob, they are allowed to do unitary or measurement, because that is the only thing you can do on a quantum state, right? So they can do this thing, and then they can coordinate the task, and then at the end of the day they will achieve something. Okay, so let us see what they can do. Okay, so in quantum communication, many things people have discovered, starting from quantum teleportation to remote state preparation, quantum key distribution, quantum internet, quantum secret sharing, quantum money, many things, over the last 30 years, a lot of things have been done. But I will not have time probably to go to all details, but I will try to highlight these two things. Okay. Okay, let me tell you about so-called teleportation. So teleportation basically is a mechanism where there is a device and somebody attends into device, and he switch on a button, then disappears and appears in some other planet. Okay. If you have seen the movie like Fly or Star Trek serial, maybe you might have seen this kind of features, this kind of fictions appear there, right? So teleportation dictionary meaning is you destroy an object, the same thing at a distant location. Okay, that is teleportation. So can you do something similar in quantum mechanics? The answer is yes, you can do that. So here is the scheme to teleport a qubit. So Alice and Bob, they're far separated. Alice could be in Delhi, Bob could be in Bombay, or could be New York, or could be on Mars, or or Moon, anywhere he likes, right? Now, before starting the protocol, they share an entangled state, and they also have access to classical channel. Now somebody comes and gives a state psi, which Alice want to teleport from here to here. Okay. And she is not allowed to send this state physically. That is, she cannot put this qubit in a box and seal it and send it by courier. This is not allowed. And sorry, and of course, she cannot read information because it's a single copy, and from a single qubit, Alice will not be able to know all the information. Okay, the only way to know a quantum state is to have infinite number of copies and do measurement of some suitable observable, and then determine the quantum state. But given a single copy, there is no way that Alice can do that. Then you may think that okay, let Alice can do copy and then know what is state psi. But then by no cloning theorem, this is again not allowed. Okay, so a priori it might look that this is not possible to teleport from here to here. But then entanglement really helps by doing something here, not knowing what is psi, by just sending two classical bit to Bob. At the end of the day, the state of Bob will get transformed to the state that psi that was given to Alice. This is the magic of entanglement. So entanglement somehow transfers all the information that is there through this channel by sending only two classical bit. The state appears here. So this is the real beauty, real magic of entanglement. And the idea was first proposed by Charles Bennett and others. Here you see Charles Bennett Wooters, Richard Joja, and then Gilles Brassard, and this Claude Creeper here. So these 6 scientists, they proposed this teleportation theoretically in 1993. And just 4 years later, this Innsbruck group in Austria, they did the experimental test. And the test was done just over over tabletop experiment over a few meter distance, but still it was remarkable at that time, And what you see here is this team that did teleportation here, and this person standing behind is none other than the Anton Jellinger, who received Nobel Prize for his work on teleportation and quantum entanglement in 2022. And this person standing here is J.W. Pan. He is leading China's quantum, quantum technology, and you might have seen in news that few years back, China, they achieved, quantum satellite. They achieved long distance entanglement distribution, quantum key distribution, all the things. This was actually the Pan group, So he was postdoc at the time, and after that, he has been leading this quantum science and technology in China for the last 20 years. And here you see the record-breaking distance by Chinese group, Pan group actually. So they teleported a single photon from ground observatory to low Earth orbit satellite through an uplink channel, which is spanning about distance like 1,400 kilometers. So this is latest record distance about quantum teleportation. And second quantum communication is something called remote state preparation, which I proposed in 1999 and it published in 2000. So what you do here is, it is similar to teleportation, but not exactly. This is a different protocol. So Alice, nobody comes and gives state to Alice, but Alice has something in her mind, and that something can be translated to a distant location using entanglement and classical communication. Okay. So using entangled state, local operation, and 1 bit of classical communication, she can prepare a quantum bit or qubit of her choice at a distant location, remote location. That is why this is called remote state preparation. And this has been also experimentally verified by many groups. So the scheme looks like this. So Alice and Bob, they're again far separated. They set the entangled state, and they have access to classical channel. So unlike teleportation, there is no state psi coming, somebody coming and giving to Alice. No, not that. So Alice has something in her mind, and depending on the state she has in her mind, she will apply some unitary to this particle, and then do a measurement. Send only one classical bit to Bob, and then the state of Bob, which was a completely random state, get transformed to the state psi. So this is again magic of entanglement. So, so imagine, let me tell you a kind of rough analogy, in day-to-day life. So suppose that Alice and Bob, they're friend, okay, and Alice want to prepare a delicious dish in Bob's kitchen, okay. So what she can do? Either she can prepare the dish in her kitchen and send it by courier, or she can tell to Bob over classical channel, like telephone call, and she can tell, okay, you do this, you do this, do this, and Bob will prepare the item in his kitchen, right? But if Alice and Bob share an entangled state, then without sending the full dish by courier, or without sending all the preparation, all the recipe, all details of recipe, by sending only one classical bit, Alice can help Bob to prepare this dish in his kitchen. Okay, so this is a rough analogy, but I thought I will tell you, just to get the flavor of this, this protocol. Okay, now coming to quantum key distribution, again, this is again vast area. So basically, what you want to do is you want to ensure unhackable key distribution, and no cloning principle plays a very important role, and that prevents an eavesdropper from copying quantum state without detection. The first protocol came in 1984 by Bernard Brassard, and then this is also BBM92 protocol. Also came in 1992, and they are very powerful, very useful quantum secure communication protocols. And eavesdropping detection is also protected by quantum mechanics, because any interception will disturb the quantum state, and that will give an alert to listen Bob, so that they can discard the round and then start afresh. So quantum mechanics helps you to establish a secure key between Alice and Bob using either direct communication or through entangled state channel and so on. Okay, so this is again a vast area and a lot of things. And these are the things that actually going to find real world commercial application. Quantum internet is again a very futuristic, but already proposed way back in 2008 by Kimball from Caltech. So basically what you do is you have a set of quantum nodes, and quantum information you can encode and process and store in local nodes. In local nodes, you can connect by quantum channel, and that can transport qubit from side to side. For transportation, you can use either teleportation or remote state duplication, anything you want to like. And then you can distribute entanglement over entire network. That will lead to quantum internet. You can download entanglement, you can download qubit, you can do computation, and you can do communication and send it back to the local nodes. So this is very futuristic protocol, but one day, you will see these kind of things happening. So quantum, sorry. Yeah, where am here? Okay. So quantum technology, as I said, is quite fast topic. Quantum computing, quantum communication, quantum metrology, quantum hardware, they're part of this. In quantum computing side, you have quantum processor, quantum software, quantum algorithm, and so on. Quantum communication side, you have teleportation, RSP, QKD, random number generation, quantum secure network, quantum internet. On quantum sensor metrology side, you have to design atomic clock, quantum gravimeter, quantum magnetometer, quantum imaging, even quantum microscope. So in all these tasks, you will see quantum entanglement plays a very, very, pivotal role, in sense that if you use entanglement, you can enhance the precision of clock. If you use entanglement, you can enhance the sensing. If you use entangled state, you can enhance the quality of image. So many things are happening. So I mean, future is really going to be dominated by quantum technology. And in quantum material side, you have to design quantum platform for quantum computing, quantum dot, quantum simulator, and there are many platforms are very promising, like superconducting or ion trap, or even NV center. Many things are coming up. So which one really is going to shape the future, we still don't know, but a lot of promise are there. And quantum science and technology, or quantum computing and quantum information, this branch, this field as a whole is, in some sense, truly interdisciplinary science, because you need expertise from quantum theory, you need expertise from computer science, you need from engineering side, you need from information theory, you need people from communication, from cryptography, you need from from condensed matter science. So many things really going to contribute to this field. So this is the field which not just I mean, you don't see only physicists working in this area. You see many you need many expertise from different disciplines. Okay, so I think I'm almost done. So let me try to summarize what I said. So quantum mechanics allows you to new way of storing information and processing information, and that was already realized by David Doyce in 1985. And quantum information technology is fundamentally different than classical information technology. And why this is fundamental? Because you have the superposition principle, you have the entanglement, you have the quantum correlation. So that makes quantum information drastically different than classical information. Okay, and once you store information in quantum state, they maintain the privacy and they provide inherent security to information stored in quantum computer. And quantum computers can perform certain tasks much more faster than classical computer. And as I said, they are very secure at a more fundamental level. And the security is not by your design, but already by nature's design, because all these so-called no-go theorems that I told you, they are fundamental consequences of quantum mechanics. It's not that you design something, extraneous. No, not that. It is already inbuilt. Once you have the quantum computer, once you have the quantum communication system, they are in place. And next revolution you will see coming from quantum computing, quantum communication, quantum technology. There's no doubt about that. Okay, so with that, I thank you all. And if you have any question, I will be happy to answer.
Thank you, sir. If anyone has have a question, please ask, or you can just type your question in chat box. Okay. Sir, Monica Singh has some question. What can be possible application of quantum mechanics in wireless communication, especially in 6G?
In where? I could not hear last part.
What can be possible application of quantum mechanics in wireless communication, especially in 6G?
So you can have very secure communication if you if you try to so-called integrate 6G communication with quantum network. They will provide extra layer of security to your communication network. Yes. Any other question?
Anyone?
Sir, I have one query. Sir, how can we stabilize this qubits in this room temperature? Can we do that?
Yeah, it depends on the physical system you use to encode your qubit. Like if you are using superconducting qubit platform, then of course you need cryogenic system. You need to go down to millikelvin or. But if you use your qubit as a single photon, like photon polarization or photon path degrees of freedom or any other degrees of freedom, then you can do it room temperature. So it depends on which platform you are going to use. Yeah.
Okay. Thank you so much, sir.
Anyone?
So all the participants are faculties or students also there?
Sir, most of the faculties, because it's FDP, so condition is they should be faculties or PG students. MTech, that means,
Okay.
or PhD scholars. You can type your if you have any query in the chat box. Okay. Dr. Priyanka Singh is asking little more explanation for no cloning theorem, if possible.
Yeah, basically, no cloning theorem applies to single unknown qubit. So what it means? It means the following. So suppose I prepare a quantum state like qubit. I prepared it. So I know what is alpha, what is beta. So I give you this alpha 0 plus beta 1, and your job is to make a copy. So your job is to make a device which will take this input and take another quantum state in some so-called, we call in analogy with Xerox machine, we call it blank state. Okay, blank state can be any state that is your choice. Could be state just 0. Okay, you take a state alpha 0 plus beta 1 and take a state 0. and then you design a unitary gate which will produce 2 copy. That means it will produce alpha 0 plus beta 1 and alpha 0 plus beta 1. Okay, this is not possible for unknown state because this alpha and beta is not known to you. Okay, as I said, to know alpha and beta, I should supply to you infinite number of copies. Okay, large number of copies I should give you so that you can do measurement of say sigma z and sigma x or sigma y and sigma z, and find the average of this sigma z, sigma y of this Pauli observable. Then you can determine what is alpha and what is beta. Okay, and if you might have seen how to represent this qubit on the block sphere, alpha is basically cos theta by 2 and beta is sin theta by 2 times exponential I phi, and theta phi what they are basically the block sphere. Theta is your polar angle and phi your azimuthal angle. Okay, so to determine alpha and beta means to determine theta and phi. So theta and phi you can determine only by measuring the sigma z average and sigma x average on large number of copies. So that is the main reason why given a single copy you cannot find what is alpha and what is beta. So basically making a copy is equivalent to knowing the state. Knowing state means you need to have infinite number of copies. Basically that is the explanation why you cannot make a copy. Okay.
Okay, sir. There is one more question from Habiba. How can we say classical computers are not more secure than quantum computer?
Yeah, because the fundamental carrier of information in classical computer are bits, whereas in quantum computer they are qubit. And as I said, classical bit anyone can copy, anyone can delete, you can do whatever you want, right? But quantum computer, in quantum computer you store information in qubit, and in qubit once you store it, nobody else in the world can make a copy, nobody else in the world can make a delete and so on. So that provides a security to information stored in quantum computer. Okay.
Okay, sir. Anyone? If I have you any questions? Okay. I think, sir, now there's no question. Okay, sir. Thank you so much, sir, for this interesting and knowledge enriching lecture. And sir, if possible, could you please share the slide with us for the participants, if possible, sir?
Okay, I'll check that. Yeah. Okay.
And thank you so much, sir.
Okay, thank you very much. Thank you.
Okay, so we will now take a 15 minutes, 10 to 15 minutes break. After that, we will begin the next session, that is session number 2. Okay. In this duration, you can mark your attendance. Next session will be taken by Mr. Lakshya Priyadarshi.